Apparently, the diagonalization of matrices it is useful, and we are going to see one specific, very wonderful application, which is commonly used, especially in economics. Now, when you say that it's especially in economics, because in that area, quantities are reasonably they reasonably converge to useful quantities. So things don't in real life, they don't traditionally diverge to infinity, or they might converge to zero if there is an exponential behavior. But because think about this one, if you have a matrix A, and this matrix A, we diagonalize this one. Let's call this one dA, which is equal to 2, 0, 0, 0, 3, 0, 0, 0, 4. Let's write this 4. Okay. Then we have another matrix P that when we diagonalize it, this can be 0.1, 0, 0, 0.2, 0, 0, and 0.4. Okay. So we have this matrix A diagonalized to dA and B to dB. So what happens if we get dA to the power n? What do we obtain? We obtain a matrix where the diagonal terms, they are expressed as 2 to the power n, 3 to the power n, and 4 to the power n. Meanwhile, the dB to the power n, it's 0 to the power n, 0.1, sorry, 0.2 to the power n, and 0.4 to the power n. So what do you observe for the first case? In the first case, of course, these are all zeros. The upper triangular and the lower triangular part, they are both equal to 0. So what we observe here is that for any quantity that increases in the same model as where xt, so for any variable where xt is equal to a to the power t times x0, these quantities, they might easily diverge to infinity, okay? Because 2 to the power n, it is an exponential increase, and the exponentially increasing quantities, we're afraid of those because they might diverge to infinity, okay? It has no sense. But then, for the second case, if we have that xt is equal to some b to the power t times x0, this one, it can converge to 0, okay? So it's better to converge to 0 than diverge to infinity. And why would this converge to 0? Because we have 0.1 to the power n. This would be 1 to the power n. So this will go to a very large number. And now there is a complete set of problems which can be described as Markov chains. Okay. So let me just write here the theory. We have Markov chains, and Markov chains, they involve Markov matrices. Markov matrices, they have a spatial construct. It's not difficult. It has a couple of wonderful properties which makes everything much simpler, which we're going to talk about. So Markov chains, there are models that include these types of matrices. Markov matrices. And the Markov matrices, the column, each column, it is the sum of each column is equal to 1. Okay, so this is what constitutes. So it's a Markov matrices. Sum of elements in a column, this is equal to 1. So here we have another condition on these, and if they are, if the sum of the elements in column is 1, then there is another property which we can talk about it later, but let's give the complete picture so that you know what we're talking about. So in Markov matrices, elements that are sum equal to 1, then one of the eigenvalues is equal to 1, okay? So lambda 1 is 1, and then lambda I for I equal, larger, and equal to 2, they are all smaller than 1, okay? So these are, so if you hear, whenever you hear about the Markov chain problems or problems that involve Markov matrices, we should remember that one of the eigenvalues is 1, the rest is smaller than 1. What does this mean regarding what we have written here on the board? If we are talking for such a system, then they look like reasonable systems to work on everyday's lives because it is also reasonable to talk about quantities that don't diverge to infinity. Okay, that's the major reason. So it looks like 1 is 1, the rest is 0, smaller than 1, so it can be quantities like these. And then what happens for these quantities which, for the eigenvalues which are smaller than 1, they all do this. Okay? So, you know why we do diagonalization? We know that exponentially increasing quantities, they increase too fast. And then, so now you understand why the Markov chains are very useful, or why, even though you are not in some fields like economics, you might hear these more than you deserve, okay? So now, let's try to deal with, let's go over an example. So I just wrote this right here in the middle. We'll leave it here, and let's see an example. Let's assume that we have 3 companies. Let's say here the market of insurance is huge, and Austrian companies, they're also huge in insurance companies. So there are Sigma and Sigad. I don't know which one is which. Sometimes I forget which insurance company I have because one is Austrian group, the other one is Vienna group. Okay, so I'm confused when we consider those. I just know that both of them, Sigma or Sigad, they are both from Austria. But now let's assume there is a competition between Sigma, Sigad, and the INSIG, okay? And the customers, they're going to be either in one or the other because it's compulsory. So then, if some customers leave one of the respective companies, they will go to the rest, okay? We don't have a fourth competitor. Then we can consider that, let's not put names in this recording regarding the names. They are all very good companies. They're good. We respect those, and we wish they give us the money back as soon as possible. So we wish they work fast and pay us the money if we have any damage. So let's call these insurance companies as Company A, Company B, and Company C. So, and let's assume that we have some customers, they move away from Company A and they go to A, okay? So let's write it like this. So they go to B or to C. So in this case, let's assume that the Company A can keep up with its own customers. So from A to A, 70% of the customers, they stay where they are, okay? And B keeps 80%. So then here we see 0.8, and here we have Company C, which is 0.5, okay? Then we can get here, this is 0.15, and this is 0.05. This 0.15, this means that 15% of the customers go from B to A, okay? So this is the mobility of the customers from one company to the other. Then here we can also obtain a 0.3, a 0.2, a 0.2, and 0.1. Now we think about the what's the name? We think about the problem, and all we care for now is that we want the what's the name? We want the columns to be equal to 1, and then the way to read this again is that apparently A loses 20% of the customers because they go from A to B, but at the same time it has received 15% of the customers of B which come to A, but we don't know the initial state of the customers of A and B, because losing 20% of some quantity, we don't know whether it's good to get 15% from B. Because B, let's assume that B0, this can be 10,000, right, customers. A0, this can be 1,000. So if 15% of B go to A, which is shown by here, this means that what is 15%? This is just, you multiply by 15 divided by 100, so you get like 150, or what is it, 10%, this is 1,500. So this 1,500, they go to A. If we read these numbers, at the same time, if A0 is equal to 1,000, then it's going to lose 20% to B, which means that it's going to lose 200 to B. So it looks like losing 20% to B is not that bad because it's going to get 15% from A. Apparently, it's a plus 1,500. It's a minus, what is this? Is wrong, 200. So in total, it's going to get this much. So the numbers, apparently, the analysis of the customers moving from one company to another, it is strongly related also to the initial state or to the initial condition. So for this reason, let's see what problem we can formulate regarding this. Give a second. Okay, so we have this matrix, and we assume that the initial condition, let's start with x0. Let's start with x0, which is equal to 0.5, 0.4, and 0.1, okay? And this is the mixture, which is, well, let's say this is the matrix, which is going to show how the companies, how the customers that belong to different companies, how they interact between each other. And now, given this initial condition, the question is the following. Find long-term distribution of customers, please. Okay, so find a long-term distribution of customers. In order to solve this problem, given these numbers, what is that we always do? In order to find the long-term distribution of customers, then it might be best if we have here the matrix A, and we have the new domain where we have the matrix D. Okay, this is the standard basis, and this is the best basis. Let's denote them like this. We have the matrix A. Let's go to D and try to solve the problem over there. So, and in order to do this, we want to find D first. So what we do is that we have this matrix here, and we want to determine what are the eigenvalues. And we immediately have here 0.7 minus lambda, 0.15, 0.3, 0.2, 0.8 minus lambda, 0.2 again, 0.1, 0.05, and 0.5 minus lambda, okay? So we try to determine the characteristic polynomial. The characteristic polynomial in lambda, P2 lambda, this is equal to, it's not P2, sorry, this is P3, because it's a 3 by 3 matrix. And if we multiply all of the diagonal terms, we're going to get a lambda cube term. So if we write this one here, we're going to get minus lambda cube plus 2 lambda squared minus 1.24 lambda plus 0.24. So this is the polynomial. Then what we can do here is that this is a Markov matrix. Then we said that one of the eigenvalues is 1. Let's see if 1 is a root. So check if lambda equal to 1 is a root. Let's do that. So we have minus 1 to the power 3 plus 2 times 1 squared minus 1.24 times 1 plus 0.24. This is equal to, this is minus 1 plus 2, that's 1. 1 plus 24 minus 1.24, this is 0. So then we say yes. So apparently, lambda 1 is a root. If lambda 1 is a root, then, so we say yes, then lambda minus 1, it's a common factor, okay? It is a common factor. What this means is that we can divide this polynomial by lambda minus 1, okay? So we can divide them like this, and we can simplify this one, because we know that this is a common factor. There will be no remainder if we divide these two together. Then if we divide these two together, what we get is that we get lambda minus 0.6. So the division, this is lambda minus 0.6 times lambda minus 0.4. This looks bad. We're going to write the complete solution here. But the polynomial is lambda minus 1 times lambda minus 0.6 times lambda minus 0.4. This is all equal to 0. So the roots, or the eigenvalues, they are 1, 0.6, and 0.4. So this theorem, which we stated initially, this holds. So this one is also true. Then what we need to do next is that we need to determine what is the matrix P. The matrix P, it will be the matrix which has the eigenvectors for the three eigenvalues, for 1, 0.6, and 0.4. The matrix is 3, 4, 1, 3, 4, 1, 3, minus 4, 1, minus 1, 0, 1. Then the P inverse, this is equal to 1 over 8, 1, 1 minus 2, 1 minus 1, 0, 1 minus 1, 0, 1, 1, 6, 1, 1, 6. Then the diagonal matrix, this is relatively easy because it's going to be 1, 0, 0, 0, 0.6, 0, 0, 0, 0.4. So this is how we can write it in here. And then the next question is trying to see how these customers move from one counter to the other. And since we know the initial condition, which is 0.5, 0.4, and 0.1, which is here, a very smart move, so this is 1 over 10 times 5 or 1, 5 or 1. So we are here at these values, and then we can immediately transform or project these values into the new domain. And in order to see how these initial conditions look like, we know that we can come to the standard basis with P, but we go backwards with P inverse, which means that if we do here P inverse times 0.5, 0.4, and 0.1, the answer is going to be 1 over 8, or 0.125, 0.025, and minus 0.05. Okay, so these are the let's say the initial condition in the best basis. Now, what we need to do here is that we need to multiply now so this is, let's consider this one, this is equal to U0. Then if this is U0, we should get that UT is equal to the diagonal matrix T times U0. So we talked about this model, and then, so this is the U0. Then here we would have the following. We have 1 to the power T is 1, 0, 0. The other eigenvalue is 0.6 to the power t, 0, 0, 0, 0.4 to the power t, times these numbers that we see here. And in fact, these numbers that, wait a second, that we find here, this is the initial conditions, yes. We need to multiply with these, but this is divided by 0.08. And from here, so this will give us the ut, but then we would have to find the xt, and the xt should be equal to the matrix P, which is clearly reported in here, times the ut. Now, if we insert any value for t, as we did in the previous case, where we inserted, for example, t, we used t equal to 4, or t equal to 3, or whatever, these are, wait a second, so here we have, we can find a precise point in time, assuming that t, or we can find this one, what happens when t is equal to 6, for example, and then we can observe what we get. Now, if we have t equal to 6, the eigenvalues that we see here, such as 0.6, 0.6, this is equal to 6 divided by 10, and this one, it will converge to 6 to the power 6 divided by 10 to the power 6. This is like approximately 1 over 2 to the power 6. So this is approximately 1 over 2 to the power 6. 2 to the power 6 is like 64. So this is like 1 over 64 approximately, which means that this is almost like 0.05. So it's like divided by 100 times 2. 2 divided by 100. So it's like 2%. So if we set a time t equal to 6, it looks like, anyways, we just tried to predict more or less how much decrease this might project at t equal to 6. Of course, we know that when t it is a very large number, this will go to 0, but this just gives us like 2 divided by 100, or 2%. Okay, so this was the way how to deal with stochastic matrices. And regarding this one, do you have any question? If you have no question, we can give another break.